Oh, this is Mr. McMurray, and we're going to make some noise today, or real sound, depending. Noise and sound is a matter of opinion. Same stuff, but it just depends if you like the music or not. Okay, let's talk about waves first, then we'll talk about sound more in particular, which is a type of sound wave. Okay, basically, anytime something moves back and forth or vibrates, it's going to give off waves of some sort. Okay, and that's called sometimes called harmonic motion, or we say the object is oscillating, which means it's going back and forth. Okay, or vibrating, same thing. It can be back and forth, it can be up and down, side to side, doesn't matter, but it's going to give off some type of wave. Now, the wave is that vibration that's given off, and it carries energy. Okay, and so the energy is what's carried by it. Okay, it's carried through a medium, which is the stuff it's going through, like the air, like my sound waves right now are going from my mouth to your to your my computer, which is recording it and then changing it back to sound waves so you can hear it. But anyhow, you get the idea. So basically, it has to travel through a medium. Okay, the vibrations have to travel through it, and the medium though is still there. When I get through talking, the air is still here where it was before I started talking, right? It doesn't all, otherwise, all the air would end up over the other direction, just like in the ocean. If all the waves were coming in, well, all the water would end up on the shore and there wouldn't be anything out in the ocean, okay? So the actual medium does not travel. It's the energy that travels through that wave, okay? Now, there are some different types of waves, and we're going to talk about that a little bit, okay? Um, and there's some characteristics of these waves, okay? The first kind let's talk about are transverse waves, okay? Transverse means they vibrate perpendicular to the direction that the wave is moving. Someone says, "Ooh, that sounds great. What in the heck does that mean?" Well, let's go look at an example. Very long spring that we have here. And it sounds perfect. So you need two people to do this good, but I'm going to vibrate this end up. That's going to be the energy input, okay? And those vibrations, you will notice, begin to travel down. Now, it doesn't travel very smoothly, but you can see that it goes up and down. Now, the wave, once I do it from my hand here, travels that direction, okay? But it's vibrating up and down this direction, perpendicular. So it's going that direction, but it's going up and down is the direction the things are vibrating. Notice the spring is still here when I get done. Okay, the matter in the spring, when the wave comes through, goes up, then it comes down, but then it's still there. Okay, the matter doesn't move, the medium doesn't move, only the energy moves. Okay, but that would be a transverse wave. All right. Now the other type is a longitudinal or compressional. Okay, now in a compressional wave, this is more like a slinky. And just I have a long slinky, eat your heart out. Okay, but here we go. And what happens is like when I talk, it compresses air molecules together. Okay, they squeeze together. That's called compression. And they're going to spread back out. Now, if I let go, you can't really see it very fast. It happens so fast, but it's going to squeeze together, spread apart, squeeze together, spread apart. And that's going to pass down all the way through the wire. So instead of going up and down, this time it's squeezed together, apart, together and apart, together and apart. Kind of like some couples. They're just together and apart, back and forth all the time. Like Ben Affleck and Lopez, anyhow, whatever. Okay, but you get the idea. Okay, so it travels through just like the other one does, and it goes back and forth, squeezing together, spreading apart. Now they call longitudinal or compressional because they move or vibrate in the same direction they're traveling. They're coming together farther apart, and they're going that same. They're going that direction, and the direction they're squeezing together, spreading apart, is going the same direction. Okay, not one direction. Well, yeah, I guess it is one direction, but there you go. Didn't know that musical group was boy band was so scientific. But anyhow, that's basically it. They're going in the direction of the wave. And those are compressional. All right. Now, waves have certain parts, whether they're transverse or compressional. They're a little bit different, but some of it's almost exactly the same. All right. First of all, depending on how hard I move that spring up and down, it's going to go far up and down or just a little bit up and down. Okay, that is called the amplitude. Okay, where it was just sitting before it started is called the resting position or resting place, or sometimes we just call that at equilibrium. It's at equilibrium. There's no force acting on it. Okay, then we go up and down. Notice if distance it goes above is the same as it will go below the resting place. Okay, and that distance from the resting place to the top or from the resting place to the bottom is called the amplitude, and it measures how much energy the vibrating particle has. The more it has, the more amplitude it will have. All right. Now, the top of the wave is called the crest, not toothpaste, that's a different kind of crest, and the bottom is called a trough, like a trough that you would put water in and water your horse or something like that. Okay, and so you have a crest and a trough. All right, notice technically which side's up. Okay, if you have a vibration coming, is it going this way or is it going this way or that way? But whatever, we'll call one side up, that's the crest, the bottom side is the trough. Now the distance from one, say, trough to another, or from one crest to another, or for that matter any other part of the wave, if this part where it's going up right here, from that spot, not there because that's going down, but to the next place where it's going up, from there to there, that is a wavelength, or how long one wave is. Okay, and that will be the same no matter where you measure it from for the same thing, but for the same wave. But it can be from any point on one part of the wave to the next part that is the same part of the wave. Okay, and that's C, that'd be the wavelength. All right, so you have resting position, how far up or down is the amplitude. Okay, now frequency is how often does this go up and down. All right, for example, let me see if I can skip my other one up here. If you look at these three, they have a different frequency. This one, when it travels this distance, has only gone up and down once. So we have a frequency of 1 hertz. It's measured in hertz. Okay, not Jalen, that's a whole different guy. But anyhow, B has a whole bunch of them. 1, 2, 3, 4, 5. Okay, so you have frequency of 5 hertz or 5 wavelengths in this length of time. Okay, and this one has about 3 or 2.5, whatever. Okay, about 2.5, really not quite 3. Okay, but anyhow, you get the idea. They have different frequencies. The more ups and downs you have, crests and troughs you have in a certain distance, you're going to have a higher frequency or in a certain length of time. Now, notice this is not saying how fast they're going. How fast they're going is this direction. The speed of the wave is how fast it's going this direction. It can go up and down a whole bunch of times and still be traveling slow or fast forward. Okay, so frequency is just how many times it goes up and down in a certain length of time, but it is not the same as how fast does it travel forward in a certain length of time. That gets a little confusing, but that is important that you understand that. Okay, now those are transitional waves, and like I said, the hertz is the measurements. AM is amplitude modulated, what that stands for. In other words, when they code the sound into it for the different radio stations, they use the amplitude. They have to do with the different amplitudes. And FM is frequency modulated, so it has to do with changing the frequency of the sound in there to make embed the little music signals or talking signals or whatever's going on that particular radio station. But notice FM is measured in megahertz or millions of hertz, whereas AM is only measured in kilohertz or thousands of hertz. So FM radio is much higher frequency than AM. Okay, and that means if you could look at the sound waves, there'd be a whole bunch of them going up and down per second. Okay, compared to that. All right. Even though they have smaller numbers, like AM tend to be 1,000 or something, or 900 and something. FM tends to be around 99 to 100, somewhere a little 80 up to 105 or something like that. But whatever. Basically, but one is talking 1,000 hertz, the other one's talking about millions of hertz. So FM is much higher frequency. Okay. All right. Now, I'm not going to worry about frequency and period. That's in the other lecture, so we'll just go on from there. All right. But once again, speed has to do with how fast it's going forward. Okay. And basically, when we're talking about sound, for example, it travels at about 350 meters, about 3.5 football fields per second. Okay, pretty fast. Not compared to light and some other ones, but it's still pretty fast. Okay, so that's what we're talking about. Speed. The speed is not how fast up and down it goes; it's how farther forward it's going. All right. So we're talking about types of waves. Let's talk about what else we got here. All right, let's talk about sound then. Okay, sound waves are produced by vibrations that are compressional, like these ones down here at the bottom. Okay, compressional waves or longitudinal waves. Instead of crest and trough where they go up or down, they have where it squeezes together, which is a compression. Compress means to squeeze together, and you have these spaces where they spread out. That is the rarefaction. Think rarefaction means rare, not close together, spread out. Okay, so they're spread farther out. Okay, and so those are like your crests and troughs. All right, and the distance from one compression to the next compression, like C here, would be exactly a wavelength. Okay, and the more wavelengths you have in a certain distance, then the higher frequency you'd have. It could be from one rarefaction to the next rarefaction, but it would still be a wavelength just like before. Now, one of the differences is you don't have the amplitude where you go up or down from a resting position, but it has to do with how, if you have a high amplitude, lots of energy, if I yell at you like that, I am compressing those air molecules close together and then they're going to spring really far apart. Okay, so when you look at the compressions, how close are they versus how far apart are these, that tells you the amplitude. If they get really close together, like when I yelled, and then they spread really far apart, that's high amplitude, okay, basically. On the other hand, if they just barely move together, barely move apart when I'm whispering like this, then they don't have much amplitude, okay? So amplitude has to do with how closely the compressions get and how far apart the rarefaction. So the closer the compression, the farther apart the rarefaction, the bigger the amplitude, more energy. If they just barely squeeze together, barely spread apart, then there's very low amplitude, okay? So it's a little different, but it's still kind of the same thing. Now, let's talk about some of these things. Basically, they are vibrations. They cause the thing to vibrate. Let's look at some of the things that we can use to make noise and sound. Once again, whether it's sound or noise, just depends on the person. All right, so here we go. All right, one of the things you may associate with sound, or you've seen before when I talk about sound, is a tuning fork, okay? And the tuning fork works very simple. You have two tines, I guess, on it. All right, and if you hit it, get a little Doppler effect there. We'll talk more about that later. You can hear it vibrate. If we put it in water, I don't know if you saw much, but the splash, probably got all of you, but okay, let's try that again. But if you stick it in here, you can see all the splash of it, that the, all right, I don't know if you can see that part, probably not real good, but when I stick it in the water, you can see the little tiny waves or ripples going out from each of these. So each of the tongs here, or tines, or whatever you want to call it, on the arms of the tuning fork, are vibrating back and forth, and they vibrate at a certain frequency. This one says it's the note of C, and that would be 256 hertz per second, or that may be, I don't know if that's kilohertz or if that's just hertz, but anyhow, that's the frequency. 256 times a second is how fast those little forks are vibrating back and forth. Okay, so a lot of sounds. All right, my computer kind of fell asleep and tried to quit on me, so I'm not sure exactly where it left off. I think I did the tuning fork, and that's where we kind of started. All right, so let's get back to instruments. Other instruments besides that, there are what we call percussion instruments. We hit, usually, and cause something to vibrate in case tambourines and xylophones and all kinds of different things, but drums would be another example. We hit the plastic vibrates. As it vibrates, it pushes air, and it makes a sound. Now, if I put it up against me, it doesn't make nearly as good of a sound, because it's kind of blocking some of those vibrations and not letting the air chamber down here resonate. And some drums are sealed off, some are not, just kind of depending on the kind of drum it is. Okay, so that's that one. Okay, there are other instruments that we have. Reeds, the woodwinds, usually clarinet, saxophone. I don't think the flute actually has a reed, but most of the other woodwinds have some kind of reed. There's also strings, which I don't have a violin or something to play, so I can't do that. But I do have this one, which is a harmonica, okay? And a harmonica is a reed instrument. So just for example, to demonstrate. Now, that's why this one is in this bag of instruments for sound, because it's getting pretty old, okay? It's been a long time. I've got some newer ones that sound a lot better, but I didn't bring them. All right, but if you look on the outside, you can see that there's a little brads on one end, and there's a little metal reed that goes the other way. And as you either breathe in or breathe out, okay, if you blow, There's some that are set inside the thing and they blow. If you suck in air, then it vibrates the ones that are on the outside vibrating. Now, the ones that have long reeds, sorry, I pointed the wrong way, these are going to not vibrate very fast, and so they tend to be low frequency, and therefore they tend to be low pitch, and that's the low sound. So I believe in them, they're low pitched. All right. With the little ones vibrate very fast, high frequency, and therefore high pitch sounds. And it plays the high notes. Okay. And so when we talk about frequency, that's what we're really talking about. What frequency do they vibrate at? And it has usually to do with the length, very often the length of the object that is vibrating. Okay. Now everywhere in the world they come up with unique ones, sounds to do different things, depending what you want to do, what kind of sound you want to get. This one, in case you ever can't go to a pep rally and they won't let you take in an air horn because they say that's too loud, you could try this. This looks like a little film canister. It has like a balloon stretched across this top with a lid on it, okay? And it's hollow in the middle, kind of like the drum, so it probably allows air to vibrate. And then on the side, it has this little hole, and you blow in, and that causes this to vibrate. And so here we go. For such a little thing, very loud. Okay, and so it worked in case of an air horn. I don't know if they'd still throw you out if you had it or make you give it up. But anyhow, there we go. So other cultures have had there's all kind of instruments depending on what people had to make them out of. They want to make something that will make noise. Okay, well, this is if you had PVC pipe and a latex glove and a straw, you can still make noise. Not a lot of noise and not necessarily pleasant. Likes to listen to bagpipes. Now you can vary the size of the pipe and the length of the pipe and get different sounds from it. But you have to have a little orchestra, a whole bunch of them set up here, and just people go down them, play different sounds. Okay. But anyhow, it's if you're ever really desperate for something to do, then there you go. That's a smaller pipe, and it has a higher pitch. Okay. One of my favorite ones, or just unusual ones, though, is this. It has a popsicle stick with two rubber erasers. Used to have a lot of these because my students would stick them on their faces when I was in 6th grade, and I would take up tons of them from certain kids every day. All right, and anyhow, then you would put a rubber band to hold those on, and you staple an index card to it. Okay, and if you spin it, I don't know if you can hear that, but it makes kind of a bee buzzing noise. Okay, I kind of like that one, kind of different. But anyhow, but there's lots of different ways to make noise. You just have to somehow create a vibration. All right. Now, not all sound waves go at the same speed. We said they go about 340 meters per second. Well, if the dry air is dry, very dry, like in a deserty area somewhere, very low humidity, it might only go 330 meters per second. Okay, so it actually go faster in moist air. Okay, it will go faster in warm air, which makes sense. When something's warm or hotter, we know the atoms move faster. Well, if they move faster already, then they're going to carry vibrations even that much better. So warm air would also make them move faster. And it depends what it's moving through. If it's solid, liquid, or gas, it will travel through faster and better. All right. Now this one you can't hear, and I don't know any way to make it where you can hear it on this, but this is just a string tied around a fork, and then you'll put this string in your ears. Okay, wrap it around your finger and stick it in your ear. All right. Now if I bang this, you just hear what you hear when silverware falls down on the ground, and it just bangs, right? But if you stick this in your ear, you will hear a gong. Okay, I promise. It just sounds like a deep gong. And it's like, whoa, a whole different sound. Partly because solids carry sound vibrations better. Okay, and so, or faster, I should say. Not necessarily better, but faster. Okay, so, for example, sound will travel 4 times faster in a liquid than it will in air. And it will go in steel, which is what stainless steel silverware is, about 15 times faster. So it's traveling a lot faster. Now, that doesn't necessarily mean it'll sound clearer or better. Okay, now say, oh, talk to me while I'm underwater. It'll be much better. Okay, no, but it does mean it will go a lot faster. Okay, and so sounds will travel a lot faster through solids, then liquids, and then gases. Now, can they travel through a vacuum? No. If you don't have anything to vibrate, a vacuum doesn't have anything to vibrate. So sound cannot travel through a vacuum. Must have some kind of medium, air, liquid, water, solid, whatever, to travel through, to vibrate. Something has to vibrate. All right. We're going to try this experiment. Sometimes it works good, sometimes it doesn't. All right. In here we have a very annoying, sounds like a truck backing up signal. And if we put it in here, it already sounds a little bit better because it's sealed. Okay. But if we stick a vacuum pump on it, and turn it on, let's see if it'll get quieter. Okay, you can still hear it, but just barely, okay? And so it does really make a difference, okay? Notice I cannot get the lid off, so it is a thing. And just to prove that, yes, it is still going, take that off and break the seal. And there it is, okay? So, that must be one of the most irritating noises in the world. They did well when they picked the signal for backing vehicles because it will get your attention. But anyhow, so that is basically, if you can create a vacuum, it will decrease the amount. Why? Because if you're in outer space, you couldn't hear things. If I was talking to you and you were in outer space, you would hear. Exactly. And someone says, what an improvement. Well, unfortunately, you're not in outer space. You're here, so you're kind of stuck. Okay. That's just the way it is. All right. But anyhow, that's kind of how that works. Okay. We're not going to worry about echoes when they bounce off a reflection of it. But basically, when sound hits a surface, it can be transmitted through it. For example, if you're sitting outside the room and you can still hear me, that means some of the sound is going through the door or the window and is being transmitted through it. It can be absorbed, or a lot of places where they do recording and stuff, they will have a lot of fluffy, irregular shapes on the ceiling and stuff, kind of like foam insulation spray that's kind of blobby, but it helps absorb sound, okay? So you don't get a whole bunch of other sound that you don't want. But if you hit a hard or sunny surface, then it's going to reflect, okay? And so the smoother it is, the better it reflects, or you get even like an echo. Or if it's more irregular, then they bounce off different directions and it's not a unified sound, and you just hopefully that distorts it a little bit. Okay, anyhow, but once again, you can look on the other one of that. Refraction of sound. Okay, sound can be bent. Refraction means to bend, and one of the characteristic of waves is that they can be bent. Okay, and here's the deal. All right, say we are in your car, and just a second. You hit a patch of sandpaper, okay? Okay, you know that really hits that shit. Say you're on your car and you drop a wheel off onto the side of the road. Well, this side is rough, okay? It's got grass or whatever. It's going to slow you down, and so instead of your wheels just going straight like they would if you were both on the pavement, now this one's going slower, so it's going to bend, and it's going to bend it and make it go that way. Okay, same way if we were on this side and we put our foot off the grass, it's going to slow us down and pull us off. And that's why if you don't have both hands on the wheel and you drop a wheel off onto the gravel or into the grass, it can whip your car over and then flip it over into the ditch and so forth. So it's going to slow that one side down, and when it does, that's going to cause your car to turn. Well, the same thing happens with sound. If something causes sound to speed up or slow down on one side more so than the other, it could be change in temperature, we talked about, or different materials, whatever, that goes through faster, then more moist air and dry air, then it can cause it to turn. Okay, and that's what refraction is, or bending of the sound. Now, this can be very important in ultrasound, which I believe some of y'all said that y'all are going to be going into in sonography and using ultrasound and stuff like that, is that when they shoot the wave through, they reflect differently depending on how hard the organ is, and it may also refract differently. And based on the way those sounds come back to the receiver, then the machine will show it up as different colors. It may depending on if it's coming away from you or towards you. For example, heart flow, a lot of times cardiac patients My daughter always had to have a sonography done on her heart because she had some heart problems, and they would show the blood flow coming to and from and seeing if it's going the right amount in the right places and things like that. And that has to do with both reflection and refraction of the sound waves, okay? And depending on how they bounce back differently, okay? Um, it's radar, we'll talk about in a minute, Doppler radar, but also kind of does the same thing. Can do it with radio waves or sound waves, either one. Okay. Now, first of all, let's talk about vibrations, though. There are what we call force vibrations, and there are resonance, and we may have heard of that. A lot of times, if you're going, your car hits a certain speed, okay, and a certain speed could be resonance or it could be force vibration. It causes the whole car to vibrate, okay. So look at an example. This is a music box. I'm going to turn it up. Hopefully you can see that, but you hopefully you can hear it. I don't know. All right, so hopefully you can hear that. All right, but if I set it down on the table, versus not on the table, okay, all I'm doing is setting it on the table or taking it off the table. All right, and what's happening is we are causing force vibrations on the thing. If I put it on the board up here, sometimes that works real good too. It almost sounds like he turned it off. And what it's doing is it's touching the board, and so when the music box vibrates, it's also causing the whole board to vibrate, which amplifies the sound. Okay, and that's a forced vibration. When one object is vibrating and causes another object to vibrate at that same frequency. Okay, and like I said, very often in machinery, in motors, things like that, you will have that. You hit a certain speed, and the motor will start vibrating, and the whole car will start to shake. Okay, fans, ceiling fans, a lot of times they seem to be a lot better now. But when they first came out with ceiling fans, if you aren't careful, they would just really vibrate at certain speeds, and you almost had to turn them off and reset it up because it wasn't vibrating. All right, and so that is a force frequency. The air inside the drum, when we hit this, it's causing the air to vibrate. So it's a force vibration. Sometimes the actual body, like a guitar, if an acoustic where it has an opening on the inside, it actually the body of the guitar vibrates, or a violin, or a bass fiddle, or whatever, cello, whatever, and it's going to cause that to vibrate, and that's a force vibration. All right. However, there is a way that you can do it without forcing it, and we're going to talk about that next. All right. A lot of objects have what they call their natural frequency. In other words, they have a frequency that they want to vibrate at. Okay? And so if you hit that frequency, then they will start vibrating it. For example, here we have 4 dowel rods with a little ball at the top, just gives it a little bit of weight. Okay, and they've been stuck into the ground down here at the bottom. That little modeling plate to hold them there. Okay, now if I move it really slow at a low frequency, they'll vibrate a little bit, but especially a tall one vibrates. Okay, so at low frequencies, remember, longer reeds vibrate at a lower frequency, lower pitch. Well, this one also does it. All right, now if I go a little faster, then the main one that vibrates is the second tallest. All right, if I go faster, I will eventually, there we go, eventually get the next to slowest. And if I'm really fast, I can make the last one vibrate mostly. Okay, it's pretty hard to do that. This next to the last one still wants to vibrate. But so at each different frequency, when I vibrate the board at the frequency that it wants to vibrate at, then it will vibrate and it will start moving faster, faster, back and forth. Okay, it doesn't matter how much, it's not like, oh, they all just move faster when I move the board faster. It depends which frequency they have. Slow frequencies, long one. The higher the frequency, these. Now, interestingly enough, and they had an earthquake in Mexico City one time, and they found out that most of the buildings that survived were 11 stories. Things were less than that or more than that tended to collapse. Okay, and they think it's because that particular earthquake had a frequency that was in tune with the 11-story buildings, and so they did not break as much. Okay, they weren't jerked forth. They were kind of in tune with the earthquake and moved at the same frequency and were less likely to break. Now, someone says, "Oh, should we make all skyscrapers 11 stories?" No, because every earthquake could have a different frequency, and so it might be a different height of a building that might survive the next time. Okay, so it's not particularly useful, but it is a good example of resonance, unless you're, of course, in the earthquake, in which case it's not a good example. I mean, it's a good example, it's just not good. Okay, now, another example is we have here two tuning forks, all right, with a box. Okay, remember the box, once this vibrates, this kind of amplifies it, kind of like we said, a natural, a force vibration, and it will kind of amplify it, just like the inside of a guitar or something like that. Okay, but here's the deal. If I hit these are both to the same pitch. We have little adjustments over here on this side. So we've got them exactly so that they are the same frequency. Okay, and if I hit this one, you can hear that. I can stop it, and this one is still going. Why? Did I ever hit this one? No. But when the sound waves from this one hit that one, they're the same frequency as this one's natural frequency, and so those cause it to automatically start vibrating. Okay. For example, just to demonstrate, if I only had this one and I stopped it, you can still hear a bit of hum from this one because it's way over here, but it pretty much stops. Okay, that's it. There's none. But if I put them together and let it vibrate, and it can work either way. Stop this one. You can still hear it. Okay, and that's what we call resonance. Resonance is one object is vibrating at the natural frequency of another object and causes it to begin to vibrate at its natural frequency, the frequency it wants to vibrate. A more famous type of resonance that you've probably heard about is wine glasses. If I get my finger wet, now ideally it works in crystal, I suppose, better, but I can't afford crystal glasses. These are just cheap glasses that I got. These two at a garage sale, these at Goodwill. Guess what? They look at you funny if you go into Goodwill, lick your finger and rub it around the top, but it works, okay? Some only did a force vibration and made the whole metal shelf shake with all the glasses on it. But if you can vibrate your finger around the top at the same frequency that the glass wants to vibrate at, it will resonate. And you can hear that. Okay, now these are the same size because they hit pretty much the same frequency. Now you have to get exactly the same amount of water in them. If I could amplify them like I did with these the wooden boxes, I could probably get this one to resonate. Okay, and to make this one resonate. Okay, but it's hard to make very much noise off of that. Okay, notice I have some other ones. Here's a big round one, and it has a different frequency. That can also have to do with how much of the glass is available to vibrate there. But also has to do with the size of the glass. If I can get this one to vibrate, it is smaller, so would we expect it to be high-pitched or low-pitched? Short ones vibrate at a higher frequency, and yes, indeed, ooh, it's a high-pitched one. It's always fun to get all of them and do them all at the same time, and they seem to kind of actually go together, which doesn't seem musically correct because they're not all the same notes or anything. But anyhow, but that's resonance. If we can make my finger rubbing on here match the natural frequency of the glass, I can make it vibrate. Now, you may have seen things where people have shattered glasses with their voices, and usually get like an opera singer or someone like that, or they can get just a machine that generates sound, and you can pick a certain frequency. Once you narrow in on the frequency, then you can do it. Now, that's the thing. It's not just how loud it is. Now, obviously, the louder it is, the more it's going to vibrate, more amplitude, go back and forth. The glass is actually bending back and forth. If you look on the inside, you can't see it, but there are little waves vibrating toward the center. You can see those little vibrations showing how fast it's vibrating. And if you can, so obviously, the more it vibrates together and away, then the more likely it is to break, because glass is not made to bend very much. And so if it has to move back and forth very much, it's eventually going to break. So you do need loud, but more importantly, it has to be the right frequency. If it's not the right frequency, it will not make the glass vibrate. Okay, and if it doesn't vibrate, then nothing. So you have to hit the natural frequency of the glass to make it resonate. And then you have to do it loud enough or long enough to get some big enough vibrations to go that it actually shatters the glass. Wish I could do that. If I could sing and hit a certain note, then I could do that. But I can't hit a note, not the same note intentionally. So I'm never going to be able to hit the natural frequency of glass. All right. All right. So that's still resonant. All right. Now, anytime you have two sound waves going at the same time, say I'm talking and you got the TV on right now, you've got sound waves that are interfering with each other. Okay. Now, interference can be positive or it can be negative, or we like to say it can be constructive or it can be destructive. All right. Let's say we have these two tuning forks that are vibrating. Okay. When their compressions are at the same time and line up with each other, then they're going to be constructive. It's going to make the noise louder. When they're off, where you have a rarefaction up here and you have a, then they're going to cancel each other out because the air molecules are trying to spread out for one of the sounds and it's trying to uh, come back together for the other one. Well, if they're trying to spread out and come back together, then obviously there's going to be a problem. They're just going to not move very much at all, and it cancels each other out. So you can have constructive and destructive. All right. Sometimes we want both. If you're in a concert hall, you want things to echo and vibrate off the walls in such a way that they are constructive. So it makes a better sound experience for the people listening to the orchestra or the rock concert or whatever it is. Okay. On the other hand, if you have noise canceling earphones, what they do is they have a little microphone. It picks up the outside noise and it makes a sound wave that is doing just the opposite, like matter and antimatter. It's like anti-sound. Okay. It's going to have a compression where the noise outside is having a rarefaction and vice versa. So it cancels it out. So it literally cancels it out. You have destructive interference. Now, if the outside noise is the same frequency as some of the music you're listening to, then it may also cancel that out. Okay, but usually outside noise is at different frequencies than the music that we're listening to. And even if it does mess up our music a little bit, it's still a lot better than having the full interference of all that sound outside of us. And so that's the example of constructive and destructive interference. All right. Now, also, this is what caused music to have beats. When you have different instruments, even if they may be kind of playing the same notes, you will see that sometimes the beats line up, and so you have a strong sound, and then it's quieter. That louder and quieter thing is due to destructive and constructive, and that's what we call the beat, okay, of the music, okay, as well as, of course, you have usually a drum or a bass fiddle or something keeping the beat also, but that's what that is, all right? Now, if you have waves that are passing through each other, they go and they come back and they hit each other, okay, we can make what we call standing waves. In other words, a wave is coming this direction and then it comes back. And let me see if I have a picture here. And if when it comes back, it's at the resting position at the same time the wave coming this direction, then it looks like the wave is just standing here, okay? Where they are in phase, they get louder. Then when they're out of phase, they are at the resting position. And then when they get in phase again, they come down. And when they reflect back, they come back. They just keep doing that back and forth and forth. This is called a standing wave. Now, where they cross and cancel each other out, that is called a node. And there's a node here and a node there and a node there. You know that, but now you know it for sure. Okay, so there's three nodes. Now the distance between here is called the antinode. All right, which makes sense. Okay, and so here we have two antinodes and three nodes. All right. Now from a wavelength, remember, going up, going down, and now it's coming back up here. So this would be one wavelength. Here would be one and a little bit extra. Okay, maybe 1.5. Okay, so there are going to be two nodes for every wavelength. So three nodes. This is going to be half a wavelength. This is going to be one wavelength. This is going to be 1.5. Okay, and so, but it's basically you have this repeating pattern where the wave just looks like it stays the same. The little cross spots here. Okay, now I'm going to try to do that. Let's see if I can do that and make a standing wave. All right. Let me get this out. My computer's doing some funny things. It keeps going out, and the camera disappears for a second. So hopefully this will hang in there. Okay, so here we have a frame, and we have a motor down here, electric motor, which we know electric motors make things spin. That's right. And it's going to spin this around. That's going to try to get a frequency where we get a standing wave. So let's see if I can get that to do just that. Okay. Now it's pretty good, not perfect, but right here, I don't know how well you can see all that. And right here is kind of a node, and that's enough. Fade again. Let me try it again. Okay, there's kind of a node here, and of course there's a node there. Okay, here's the anti-node where as it vibrates around, you're getting this. This is where it's wide open, but they always have a node right here where they cancel each other out, and then there would be another node somewhere down there if we had room for it. Okay, so basically that's kind of what we call as a standing wave. All right, I would try it with the Slinky, but you kind of got to have two people to do it. But we may try that anyhow, right? Life is short. Difficulties here. One is, can I do it with just me? And then two, can I get it where you can see it? And I don't know if I can get it good enough that you can see. There for a second, maybe it was. That was pretty good. Okay. But at any rate, you try to get the same repeating pattern where you have a node is always in the same spot, and on each side you have where it's going up and down on either side of it. But anyhow, you get the idea. That is a standing wave. Okay. Now we also want to talk about the Doppler effect. All right. So just a second. Let me get some stuff, and I'll be right back. All right. Normally, say you have something of sound right here. Let's get something that makes some obnoxious noise here. I just happen to have something. Lots of obnoxious noises. There, how's that one? Okay. It is sending out vibrations in all directions. Think of like if you drop a rock in a puddle, it's going to send waves out in all directions. Okay. And as long as it's standing there, each wave is going to be the crest from the wave in front of it, the little ripples, if you will, are going to be the same distance apart. All right. If it's standing still. But if it's moving, so it sends out a wave here and then it's moving closer, it's going to get them all crowded together in the direction it's moving. They're going to be closer and closer together. And if they're closer together, that means they have a higher frequency. And if they have a higher frequency, we know they're going to have a higher pitch. And so they're going to be a high pitch. And so sounds of objects that are in motion sound different than if they're still. Okay? So for example, if we go back to our annoying, I'm going to call it the mosquito sound, but here we go. Get that one. That's it. But if I bring it close to you and far away, this is how you can tell when a mosquito is about to get buzzing and landing on you. Why? Because it's coming closer. And so as it comes closer, it has a higher frequency. As it goes away from you, it has a lower frequency. And so we can hear that. We hear the mosquito buzzing in for the kill sometimes, okay? And that's basically it. Now, we can't put this inside a ball and throw it back and forth, but since you're not here, that's not really going to help much. But you get the idea. Put in there. Same thing. You get that same effect, and that's called the Doppler effect. This is also how, with using radio waves instead of sound waves, which are a lot less annoying, the highway patrolman can stop you. Why? Because he's sending out radio waves. Well, if they bounce off your car as you're coming toward them, it's bouncing them closer and closer together, so it reads a high frequency when he reads those waves coming back to his radar gun. All right. If you're going away from, then they're going to be farther and farther apart as they bounce off, and because you're moving farther away for the next sound wave, so they get farther and farther apart, and they would read as a lower frequency and therefore a lower speed. And this is how they know how fast you're going. Okay. Anyhow, but that's kind of basically how that works. Now, let's see. Let's do a couple other demos, and then we'll be ready for some of the finales here. All right. This one is just a. Hopefully you can hear that. I don't know how well this will do over these speakers, so I'm going to scoot this up really close, just hoping that you can. took off without me there. I don't know what I was doing, but anyhow, hopefully nothing embarrassing. Okay, anyhow, here we go. We always need some fire. Life is always better with fire, right? So we're going to get a propane burner, okay, and we're going to light that. Now, to try this out, we have a pipe here, and in the pipe, I don't know if you can see that or not. No, probably not. Huh. I always thought you could see it. But anyhow, there's a piece of wire screen in there, okay? And we're going to heat up the wire screen. It's really hot. I'm going to put my hand down here so I don't get hot because it will conduct the heat. We learned that a couple weeks ago. That'll conduct heat very well. And I probably should have brought a hot glove, but I didn't. That's okay. All right, so now I'm getting it really, really hot. And then I'm going to pour this, see if there's any sound in it. Oh, there's some sound. Oh, let's pour all the sound out. Oh, no, there's no sound in it anymore. Oh, that's too bad. See if there's any left. Oh, we refill it. That's right. And then we'll pour some more sound back out. Oh, pretty cool, huh? All right. There's a unique instrument to play, right? Okay, everybody wants to play the pipe now. All right, it's just a metal pipe with metal screening in the bottom of it. But why does it turn on and off? Well, we heat it up. What do we know hot air does? Hot air rises. So the air rises, and as it comes through, it whistles basically through the grating that's down inside there. Okay? And so it whistles as it goes through. But when I turn it sideways, the hot air rises. Well, this means it goes up to the top, and it doesn't go through the grating anymore, so no whistling. And therefore, we can turn it on and off. Now, what if we got other pipes? Bigger pipes. Okay, we also have stuff in it. Okay, let's heat it up, see what it does. You should be able to tell me something, make a good prediction. What kind of noise will it make? Oops. Whoa. And once again, it turns off. Or it turns back on. And hopefully, you thought, oh, it's a longer pipe, therefore it will have a lower frequency and lower pitch. Alright. Which brings us to our last one. What if we had even a bigger one? There has magnets. Okay. Oops. That one got a little shifted. Let me get it back in there so it'll stay in there, right? Hopefully. Very deep. All right. Like a foghorn almost, doesn't it? So once again, longer column of air to vibrate, and therefore a lower pitch. Okay, now, logically then, if I got a really tiny one, it might do a high-pitched one, but it also has to do with standing waves and how it vibrates back and forth in the air column. And so there is limits on how small you can do that. And to be honest, most of the time I've not been able to get this one. So apparently it's just too short to get waves that will resonate. But you never know. Let's see. Maybe it's just I can't hear it. I don't have good hearing and I can't hear high frequencies. Sometimes I think I can almost hear a sound there. Maybe it's like a dog whistle. All right, ultrasonic at the higher, or not ultrasonic, at the high frequencies that dogs can hear, but we cannot. I don't hear it. So I'm assuming that it's just too short, and there are limits on how short the pipe can get. Okay. In fact, I made sure that these were in increments of one pipe. The original pipe that I did was the first one we had. Then I made the other pipes by just cutting off another piece of pipe, twice as big, and then 3 times as big. Okay. Unfortunately, this one's half as big. but that may be too small. It may be less than the standing wavelength, and so it may not work. All right, because of that. At least I haven't heard the sound yet. Maybe you heard it, I didn't. Okay. Speaking of which, that was one of our topics, though. Sounds that are too low a frequency. Okay. Below 20 hertz, 20 hertz, they're too low for us to hear, and those are called infrasonic. Okay. Whale songs, a lot of their song and stuff we can't actually hear because it's below what we can hear. And ultrasonic are things that are too high pitched, like the dog whistle, that we can't hear. Okay. All right. So, let's see. I was thinking there was one other demonstration before we do that. No, maybe not. Okay. So the last thing we're talking about is a sonic boom. Okay. We talked about if we were doing. Let me see if I can get back on here and show you one up there. I don't want to spend a lot of time on this because I know it gets explained in the other thing. Let me see. There we go. Okay. Basically, we said if an object's staying still, then the waves just go out in equal circles. If you're moving, they get closer together. Well, if you're going at the speed of sound, that means they're always going to be, you're going just as fast as sound waves are, and so these sound waves are going to start building up. Kind of like if you're in a boat and as you go through the water, starts building up these big waves at the front, and it sends out these waves off to the side. And these are ones that come if you're on the shore and come mess up your fishing line and everything. But anyhow, what if you go faster than? Well, if you actually go faster than, then you start putting higher and higher like this, and you get these building up of sound waves and pressure on the side, and you make like a cone of high pressure sound. Okay, you're actually going faster than sound, so you're going supersonic jet. Okay, now the deal is that you have this high pressure area of all these sound waves that are building up each other, and it makes like a cone shape. All right, so as you're going across the ground, where this cone touches the ground, if you were standing right there and you hear that big high pressure area, you hear a sonic boom. Okay, and the sonic boom is that high pressure sound waves that you see. Now, if you hear it or it rattles the windows and you run outside to look at the plane is going faster than the speed of sound, so he may already be out of sight. And very often you can't see the plane because he has already headed out of sight. By the time the cone crosses where you are on the ground, he's so far ahead that you may not even be able to see it or not. But that's basically what a sonic boom is. As you're going faster than the speed, so it makes this little V shape or cone of high pressure sound, and that's why it can rattle windows and even break glass and things like that sometimes. Okay, now we are going to make a sonic boom of sorts. Now, whether it's exactly a sonic boom or not, it is pretty loud though, and we'll see how well it works over the video. All right, to do that, we're going to have to come over here. Let me switch back to full screen view here. All right, and let me just show you what we're doing here, our setup, if you will. All right, we have a bottle, has a hole in the lid, just a little tiny pinprick. It has a hole in the bottom, and it has a tube going up inside of it. The tube is attached to a flask, which has zinc, silver metal in the bottom, and we're going to pour hydrochloric acid in it. This is the same stuff, if you remember back when we blew up the Coke cans, we needed some fuel, so we used that. But we're going to try to make some hydrogen gas. All right, so we're going to pour that in there. It's starting to fizz and stuff. All right, I'm going to put a little bit more in there just to make sure we have plenty to do the reaction here. Hopefully before long we'll see some of that coming out the other side and coming out the top here. That's good. All right. Now this is hydrogen gas, but it turns out that hydrogen gas, pure hydrogen gas, doesn't burn as well as if you have a mixture of oxygen, which is in the air about 18%, and hydrogen. Okay. Now we're getting a pretty good cloud built up in there of hydrogen gas. All right, we're going to let it go for a little bit longer. Make sure we got plenty of hydrogen. We want to force out all the other gases that are in there, and so forth. All right. We can even put our finger over that to help build up the pressure a little bit. definitely coming out the bottom. So I think we're probably pretty good. We're about ready to go. We're going to turn off the lights just to see if that helps what we can see or not. We'll see how it works for you. Okay, I'm going to take the hydrogen gas source out. Oops, just broke out. That's okay. All right, and we're going to put it over here so the fuel is out of the way. And we're going to light this. Now, you see a little poof, a little flame there, okay? So it's burning the hydrogen gas, which is lighter than air, so it's going to kind of rise up the top. Now, theoretically, they say you should hold your hands in front of your ears if you were actually here, and because it is such a sonic boom that it could actually hurt. Now, so it will burn that, but as it burns out the hydrogen gas, you get more oxygen and less hydrogen. Somewhere, it's going to hit the ideal mixture. Usually, we hear a whistle, we get tired and think, oh, it's not going to do it, it's not going to do it. And then all of a sudden you hear this little whistle, and that means the end is near, but we'll see. We got just a little bit of flame up there still going. So let's see what we get. I'll put my hands in front of my ears because I'm old and can't hear very good anyhow. I don't want to go deaf. Still burning at the top. Haven't heard any sound yet. There we go. Hear a whistle. There you go. Pretty good, pretty good. I don't know how long this plastic bottle is going to last. I've had it for 5 or 6 years, but so far the lid of it is very white and looks like it's been melted almost, but it hadn't lost its shape, and so we keep hanging on to it. One of these days I'll have to see if I can replace it or not. Anyhow, that's it. That's our sonic boom. All right. Other than that, I guess have a good week. Don't forget to get your questions done and take your quiz. All right. And we'll talk to you next week. Have a great week.